All right, for the last topic in Introduction to Calculus, we're going to talk about what we've been doing as far as approximating the area under the curve and what it is leading up to. Up until now, what we've done is we've had some curve, and you know, it looks really weird and whatnot, right? And then what we've done is we take that curve and we approximate it. We approximate the area underneath by drawing a bunch of rectangles. So that the first time it's the top left corner of the rectangle that touches the curve, and then the next time it is the it is the top right corner of the rectangle that touches the curve. And so we get two estimates, and we talked about taking the average of those estimates to get something that's even closer. And in fact, that's kind of like filling in the area with trapezoids instead of rectangles. If you were to take the average, that would be like filling it up with trapezoids. So there's a little hint for you. All right, so you fill it up with rectangles and you get something that is really, really close, and obviously the more rectangles you have, the closer your estimate is. Well, let's just look at what each rectangle is. Well, each rectangle has a width of delta x, which I'm calling some change in x. That's my width. And then the height of each rectangle is some f of x for a different x. So I will call each of those x's, you know, xi. Okay. And I'm adding all of those together. Okay. That was kind of a funky summation symbol there. But that's kind of what I'm doing, is I'm adding together all of these widths and heights to get something that is close to the approximate area under the curve, where f of xi is the height and delta x, which is some small change in x, is my width. So I'm adding those together. All right, so it looks like that. All right, so I'm summing as x goes from a to b, and then so you take the function value and multiply it by the width. All right, so that's what we've been doing up until now. Well, sometimes you can take the exact area. But before we talk about that, let's talk about how we get closer and closer to that exact area. Okay? Well, as I am adding more and more rectangles, what happens is the width of each individual rectangle gets closer and closer to 0. Obviously, it doesn't get there because every rectangle needs a width, but we can see what's happening as the width of each rectangle approaches 0. So that, as we've talked about before, is a limit. And this just looks like the line before, but I've said the limit as delta x, which is my width, approaches 0. All right? Well, when that happens, what we call that, or the notation for that, is this. With that funky little s in front, my lower and upper limits are the same, f of x is the same, but now since delta x is approaching 0, we're going to say that that instantaneous change in x, instead of just being a small change in x, it's going to be an instantaneous change in x. That's going to be called dx instead of delta x. That's just notation. Okay, and what this is called the definite integral. All right, and the definite integral is what I use to find the exact area. This summation was an approximation of the area, but once I take the definite integral, that is the exact area underneath the curve. Okay? It is the exact area between f of x and the x-axis from x equals a to x equals b. Well, great. That notation doesn't help me very much because I still can't do questions like this, where I've got a function y equals x squared plus 1, and I'm asked to figure out the area from x equals 1 to x equals 2. I would still have to use little itty-bitty rectangles to approximate the area from x equals 1 to x equals 2, because I don't know how to calculate the area from that curve to the x-axis. Okay, so I would still have to use rectangles. But there are some situations where you can look at the graph and you can say, oh, I know how to calculate the area of that shape. So that's what you do. Here's an example of that. Suppose instead we have the function y equals 2x plus 1, and I want to know the area between the curve and the x-axis from x equals 1 to x equals 3. Well, that shape Oh, here. That shape, I can represent that area like this. Right? That's the area that I'm talking about, the area between that slanted line and the x-axis. Right? There's a slanted line, there's the x-axis, from x equals 1 to x equals 3. That's the area that I want, and that's what this question is asking. The area from the function to the x-axis, where that's the function, as I go from x equals 1 to x equals 3. That's that area there. Well, I know how to calculate the area of that shape. That is a trapezoid. So you just use the formula for the area of a trapezoid to figure out the exact area. And that area is, well, let's see if you remember the formula. It's 1/2 times base 1, this we'll call it base 1, which is 3, plus base 2, that's base 2, and that's a 7, times the height. And this along the horizontal is the height, a height of 2. So that area is actually 1/2 times 2 is 1 times the 10 is 10. So I can do a lot better than approximate the area under this curve. I can actually calculate what it is exactly, and that is 10. So the types of questions I'm going to give you for now are, if I'm asking you for this, I will give you a shape that you recognize, and you can actually calculate the area underneath it. If you can't do that, then it's an unfair question for me to give you at this point. Eventually, we'll be able to do this for any curve I can come up with, but that's later on in the calculus chapter. All right, so here's one. It is the function the square root of 9 minus x squared as x goes from -3 to 3. Well, if you graph that, you should recognize that that is a semicircle, half a circle. And I know the formula for the area of a semicircle. That is 1/2 times pi times r squared, where the radius is 3. Right? So that's going to be 9 pi over 2. That's the exact area under this curve. I could approximate it using rectangles, but why do that when I can come up with something that is exact? Okay, so that is just a short little mini lesson on some new notation, definite integral notation, and how to use it when you can actually find the exact area underneath a curve.